Our first speaker this morning is Rama Kandasamy, who's a paediatrician and immunisation specialist at the Sydney Children's Hospital, a senior lecturer at the University of Sydney, and holds an NHMRC Emerging Leader Fellowship grant, as well as a lot of other impressive achievements I'll get you to have a look at. And the first talk is titled Pneumococcal Disease and Vaccination, Past, Present and Future. So welcome.
Thank you. So I'm going to give a relatively brief overview of probably what's a relatively complex topic, but I'm going to focus on the paediatric population in Australia and give a real sense of what's been happening in terms of our vaccination program for pneumococcal disease and some of the challenges that are on the horizon, how we might try and approach and solve those. So pneumococcus is a gram-positive diplococci. It has this outer polysaccharide capsule or sugar coating, which we use to classify it, and it's really the antibody recognition of that sugar capsule which we use to classify or call it serotype. And there's over 100 different serotypes being described so far, and it's important in terms of those serotypes to understand that we only target some of them with our vaccines to date. And there's definitely a predisposition for some of those serotypes to more likely cause disease than others. Now, pneumococcus is well known to cause pneumonia amongst children and also meningitis, and it's the biggest bacterial cause of pneumonia and meningitis amongst children around the world. It has relatively low antibiotic resistance patterns here in Australia, and so fortunately we can still have beta-lactams as our primary line of treatment for community-acquired pneumonia. It's important to note, though, in the context of meningitis, even with installation of prompt antibiotic treatment, you can still have quite significant outcomes, including death from pneumococcus. The burden of disease around the world is quite substantial. Although these numbers are a bit dated, they're still quite alarming. We have, from these estimates back in 2015, nearly 9 million cases of pneumonia amongst children, 80,000 cases of meningitis, and about 300,000 deaths amongst children under 5 years of age. Importantly to note, similarly from this paper, is that with growing vaccine coverage, you see declining mortality due to pneumococcus. And I think that the real number in terms of deaths amongst children under 5 years of age is probably closer to 200,000 per year. It's important to understand the interplay between asymptomatic carriage and pneumococcal disease, because this is where the conjugate vaccines really work to interrupt not only transmission and provide herd protection, but also prevent disease directly in the person receiving the vaccine. Carriage is an important aspect to understand with pneumococcal disease. It is the obviously acquisition asymptomatically usually of pneumococcus that then leads to either local disease developments in the respiratory tract causing pneumonia or more extensive invasion causing meningitis and septicemia. Carriage is amongst children relatively common. About 1 in 2 children under 5 years of age will have pneumococcus found in their nasopharynx if you swab them. And I'll get you just to think about whether that's the most important reason why we vaccinate children across a population. Is it to create that herd protection to those people that aren't able to be vaccinated or who are under-vaccinated? Pneumonia due to pneumococcus is the most significant disease burden, although it's very difficult to measure. We don't have a diagnostic test really for pneumococcal pneumonia, but we know it's not infrequent. We estimated from essentially post-vaccine epidemiological studies that about 200 per 100,000 children will have pneumococcal pneumonia, and that's in a post-vaccination context similar to ours. I like to think this might be also one of the main reasons why we use pneumococcal vaccines across the population, because of such the significant burden of disease we see due to this clinical outcome. Invasive disease, as you're aware, is very severe. It's infrequent though, but still not infrequent to ignore, not so infrequent to ignore. So we see it about 20 cases per 100,000, which is still more frequent than meningococcal disease. We surveil it relatively well here in Australia, and so we have a good sense of exactly what serotypes are causing invasive pneumococcal disease across our population. I'll touch on some of that data in a minute. What are the vaccines and how have they evolved over time? Well, in terms of conjugate vaccines, they essentially started off with a 7-valent vaccine, which was licensed and used across many resource-rich settings before the high-valent 10 or 13 vaccines were then introduced, and that's what we saw in Australia. You can see there that they're essentially built upon that same backbone of the 7-valent polysaccharides in the PCV7, just with additional serotype coverage as you go down the list. Importantly, you can see that PCV15 and PCV20 there have the same backbone, are now licensed in Australia, but are not funded at this stage. You can also see perhaps there's a bit of a shift in strategy with that PCV21 vaccine there, covering a broader set of serotypes and not having that underlying PCV7 backbone. In Australia, as I said, started off with PCV7. We're delivering it as a 3-dose priming schedule with no booster for a good 6 years across the entire population. We then moved on to the PCV13 vaccine there in 2011 with the same schedule. A bit more recently, in 2018, we changed the schedule up to just have 2 priming doses and a booster to try and give us a bit more persistence later in childhood. And that's the schedule we're still using with PCV13 at the moment, although there are recommendations around PCV15 and PCV20 that they're not funded at this stage. Important to note across Australia though, disease is not uniform. We see high rates of disease, as you see in that map there, across settings where there's higher populations of Indigenous peoples, and that's why there's recommendations there to have additional doses of conjugate vaccine for those children, and then also additional doses of this polysaccharide vaccine later in childhood. So how successful have these vaccines been? So first of all, when it comes to pneumonia, like I said, very hard to measure, but we can try and measure at least all-cause pneumonia across hospital settings, and this is what this paper has shown, that essentially in the pink bar with Indigenous children here in those first bars, you see a decline from prior to PCV7 introduction to after PCV7 introduction. Similarly, in non-Indigenous populations, you see this decline, although not as distinct in the Indigenous population since the introduction of vaccine. What this table shows is essentially different phases of vaccination. So initially we actually targeted Indigenous children, so that was that phase there. Then we gave PCV7 to all children, and so that's this next phase here, and then we gave PCV13. And so what we're showing here is essentially hospitalisation rates due to all-cause pneumonia clearly declining over each of these phases. And similarly, even in under-vaccinated or unvaccinated children, we're seeing a decline as well. This is also showing pneumococcal confirmed cases, obviously a lot more infrequent because you need to do invasive testing usually to do this, but showing the same trends in both contexts. What about invasive disease? Like I said, we measure this a little bit more accurately, and we know specific serotypes that cause it when we pick them up. And so importantly, you can see here, I want you just to focus on the black line to begin with, that after PCV7 introduction, rapid decline before levelling out in terms of the amount of cases of disease occurring. Before introducing PCV13, a little bit more of a decline, before what seems to be a bit of a trend up with this caveat here of COVID, and then also the change in schedule from a 2+1. So it probably need a little bit more time to see what the overall trend is here. But still we're seeing this trend of at least non-vaccine type disease, which is this green line here, representing most of what this black line is. There is still some residual vaccine type disease, and I'll touch on exactly what these breakthrough cases are amongst these children here. So looking into those breakthrough cases on this first graph here, you can see that they've been increasing in number over time, and that's also with vaccine change. And they're broken down by age group here. I'll get you to focus in on the green, purple, and even the blue bars, and you see those kind of expanding over time. COVID's messed up our data, but it seems like perhaps they're expanding again over time. When you break down these breakthrough cases of disease, they're largely represented here by this black bar, which is serotype 3. And this graph is just showing the proportion by serotype of those breakthrough cases. And so by far and away, serotype 3 is the cause of most of these breakthrough cases here. What about the other serotypes, the non-vaccine types? And as I said, these are the ones that are explaining most of the disease incidence now in terms of the invasive context to date. You can see here we have a real snapshot of the kind of main serotypes responsible for non-vaccine type invasive disease over these kind of or the 10 years from 2011 to 2020 at least. And you can see that the dominant ones are over here, 23B and 15C, and then you've got a range of others also causing, not insignificant amounts of disease. Importantly, we're interested in which ones are covered by these newer licensed vaccines in our setting. You can see there that PCV 15 and 20 pick up a number of these serotypes that are meaningful in terms of their incidence in our population. Another little insight we're thinking about also is the age group where we're seeing disease. And so I've taken some of the publicly available data that we have now on our national disease dashboard, and I've just looked at the age grouping we have for it. And you can see here, if you group by age, by your 2 to 4, your 5 to 10s particularly, and so the dark blue and the light blue bars I want you to kind of zoom in on. You can see those are expanding over time periods for those breakthrough cases. So these are vaccine type cases, which I explained before. And this is indicative that these serotype 3 cases are more commonly occurring in this age group. And then if you look at non-vaccine type cases, you can see that also there seems to be disease numbers increasing in those slightly older age groups. And so that's worth thinking about when we come to introducing new vaccines and the timing of them. What about the future? So I've alluded to some of the problems. Obviously, there's a growing need to adapt to ongoing emergence of strains not covered by our vaccines. Although that gives us, I suppose, a bit of a short, medium-term intervention, and there continues to be probably this emerging problem of emerging strains of non-vaccine types that are not covered by whatever vaccine we're using across a population. There's a growing body of evidence that there's expansion of this disease also within this slightly older childhood group, and we need to think a little bit laterally about how we're deploying the vaccines we're using at the moment and whether we can also try some more novel approaches such as using vaccines which cover slightly different patterns of serotypes in this age group. There's some work on having better diagnostics for children coming in with febrile illness, and so this is one example here which I'm hopeful might be translated to the clinical space. And so using gene expression signatures, they're able to very accurately determine what is the cause of your fever in any given case. And there's an example there of a child with respiratory infection who has greater than 90% probability of having pneumococcus as the cause of the illness just based on their gene expression signature. Similarly, there's a children there of a fever of unknown source who has a high probability of having juvenile arthritis just based on this gene expression signature. So using those kind of data, not just at the clinical space, but also as an epidemiological measure, may be something we'd be able to use to get a better handle on exactly how much pneumococcal pneumonia is occurring in any given setting at any given time, which we just don't know at the moment. And then in terms of pneumococcal disease, it's not just a pathogen-based phenomena. There's aspects clearly due to the pathogen that relate to disease causation, but there's also human-based factors, particularly human genomic factors that make you susceptible to disease. And this is an example of a GWAS I've done of people who have a history of childhood pneumonia, showing that there's a variance in the genome of genome-wide significance that are related to your susceptibility of developing disease. And similarly, I'm working on one for invasive pneumococcal disease. Using those kind of outputs may help us screen for people across the populations and identify those who are at increased risk and perhaps tailor preventive measures to them. So in conclusion, PCV has obviously been very effective in our population in reducing invasive disease. It's a little bit less certain about pneumonia across our population, largely because we don't have an accurate diagnostic. but there's clear data that all-cause pneumonia has been declining with progressive intervention of the various vaccines across our population. Obviously, there is some work to do. There's increasing numbers of disease when it comes to non-vaccine type disease, particularly in preschool-age children, I think, and we have to continue to monitor those trends and adapt accordingly. It's important to note that pneumococcus is highly adaptable to clinical interventions, both antibiotic and vaccine, and it will continue to be so. And so we need to continue to develop and evolve with it and try and stay ahead of the game. Like I said, we need to think about perhaps the human genomic factors as well and start to tailor approaches we use when it comes to preventative measures. So I'll conclude my talk there. We have time for questions?
Fantastic. That was a great talk, and we're a little bit ahead of time, which never happens at this meeting, so there's plenty of time for questions, which is good. And we've already got some coming in online, which is fantastic, but I'd encourage people to keep submitting those. So if you could just raise your hand, we'll run over a microphone so everyone can get to hear. I think there's a couple over here we might start with, and then one down the front.
Thanks, Rama, for a talk. Being someone at the other end of the age spectrum, it's a pity not to see something on older populations as well. That might get picked up at the panel. My question is that we expect something like 8 to 10 times the number of respiratory infections like pneumonia, but we just don't have the various measures to assess that. Could you briefly comment on the advance of that? Because I know that the various vaccine manufacturers have got some urine assay tests very focused on their serotypes, but for decent, in terms of surveillance, it would be really helpful for all of the prevalent strains in Australia that we actually have that, both for the younger population and for older. So what's happening in that space and how soon is it likely to happen?
So I suppose in the antigen detection space with regards to urine samples, it's, as you may be aware, it's a test which is useful in the adult setting, in the older adult setting particularly, because there's low rates of asymptomatic carriage within that population. And I think if you use that test in a particular, you've got a particular clinical syndrome in front of you, then it has pretty good accuracy. It doesn't have the same utility in the younger population due to the high rates of asymptomatic carriage. So you do pick up a lot of probably incidental carriage of pneumococcus, but it's not the cause of their clinical syndrome in front of you. And so that's the challenge with that test.
But the bigger issue is there's only a limited number of serotypes, and we actually need that to be expanded.
Yes. So potentially expanding that would have utility as not just a diagnostic in that context or a surveillance tool in that context, and it would be much more useful as a broader surveillance context. I agree. You'd have to talk to Pfizer about whether they're expanding it. To be honest, they keep it under wraps and we're usually the last to hear about it. But I haven't heard anything in the works at the moment in terms of expanding the number of serotypes beyond what they already have. Yeah.
Don't hold us in suspense. What are these genetic pathways? Are they innate, adaptive, immune, or other?
Yeah, so I suppose in the genome-wide study I showed there, one of the big peaks was actually in the HLA region. Some of the other areas, I suppose, we need to functionally work out exactly how they are related to disease causation, I think. But yeah, the HLA one is the big peak there. Yep.
Thanks for a very nice talk, Rama. I guess one of the issues in terms of looking at those older children getting invasive pneumococcal disease quite frequently is complicated pneumonia with empyema. But I think if we really want to decrease the rates in those older children, I think having a catch-up campaign, if we implement a greater valency, whether it's 15 or 20 valent, would probably be what we would need just in that sort of preschool population, because I think that's what delivers that herd immunity that you quite nicely showed. And just to plug for the talk this afternoon, I think preventing RSV is also a good way of preventing pneumococcal disease, and I think there's some good examples of that during the pandemic where that occurred. So there's a few other ways that we can perhaps look at decreasing invasive pneumococcal disease? Because I guess we really, over the last 10 years, haven't had a big impact on overall rates of IPD in children, which is a bit disappointing.
Yeah, I agree, Peter. I think there's a number of moving parts to this puzzle, and RSV is just another one of them. And this talk could be much longer than it was. And so yeah, watching the trends, I think with obviously population rollout of RSV, preventative measures over these coming years is going to be very interesting. And obviously we're looking to the Northern Hemisphere to see what those trends early on might be reflected down here, I suppose. But I think, yeah, thinking about how we can provide better coverage in that slightly older childhood group is something worth pondering upon. I think there's a few ways to approach that, and even potentially new tools to kind of try and combat that with. And so there's probably going to be a number of different approaches that different regions actually take. Yeah.
Hi, I'm hoping I've got some good news to disseminate, but Adelaide University researchers are working with GPN vaccines, also in Adelaide, and we have this vaccine in theory should work against all strains of strep pneumoniae. It's a very clever bit of research, which I'd happily tell anyone about later if they're interested, but essentially it's the bacteria without its polysaccharide, coat, and it's, a whole cell vaccine, and it seems to be working against all the strains.
Yeah, so that's those kind of novel approaches are things that we need. I think potentially using something like that, which is looking beyond the capsule, has utility across many settings. Perhaps using that in combination with a polysaccharide-based platform as well is also a novel way of trying to cover all of those virulence factors that pneumococcus has. But yeah, excited to see how things pan out for it. Shamez? Yeah.
Oh, hi. Nice to meet you finally. I think I've known you for like 10 years, but I don't think we've ever met. My name is Shamez Ladani. I actually lead the pneumococcal surveillance in the UK. I just wanted to add a little bit to what you said. Everybody's working to expand the serotypes. Each company is focusing on the serotypes that are coming in the new vaccines. It's a 20-valent, there's 24-valent, and there's 30-valent, and they're all working really hard because all of them realize that actually the biggest indication that they have for the vaccine is for pneumonia over invasive pneumococcal disease, and to show a reduction in pneumonia, they have to do the urine antigen tests and serotype-specific urine antigen tests. It's very complex because there's a lot of noise that they have to get rid of, and they're all struggling. And every time you add a serotype, each serotype has its own complexities, and it's often difficult to distinguish within that serogroup whether it's a serotype that you're interested in. But they're all working on it. We're working on it as well. We're working on a 30-valent, 32-valent, I think, to look at 32 serotypes in the urine antigens that we're doing. So that will move ahead, but it's a really mucky system. But for the purposes of licensure and pharmaceuticals, I think it will get done because of its priority, but they'll focus mainly on that issue. The other question about the booster, I really do hope you're not going to start boosting everybody with the conjugate vaccine. That's not how it works. The problem that you're seeing is just trends, and most of your trends will be, without even knowing, would be serotype 3, 19F, and 19A. That's because the vaccine is not really good against those serotypes. It's not the kid. It's the vaccine that doesn't protect as well. So the best way to do it is to make sure you have very high uptake in children and maintain herd immunity, and that will protect your older children as much as it will the adults. The increase you're seeing, funnily now, especially with serotype 3, is something we're seeing in the UK as well, and we panicked because we started a 1+1 program, and as soon as we came out of the pandemic, serotype 3 just shot up. At one point, it was responsible for 1 in 6 of our infections across the country. And after a year, it stabilized, and then now it's gone down again. It had nothing to do with the program at all. It's just doing its own thing. And therefore, it's one of those where actually you just have to keep an eye on it. If it's any of the other serotypes, then that would be interesting. One of the things that we've found in the last 5 years is serotype 4 has increased. Serotype 4 was almost disappeared with PCV7. Now it's come back, but only in adults. You don't see it in children at all. And we don't understand why a vaccine serotype is circulating in adults without affecting children. And it's really worrying us because we don't know whether it's loss of carriage in children that allows adults to get it, or whether it's circulating in adults and we're never going to get rid of it without vaccine. And the final thing about your program is there is a problem. People are getting concerned about messing the nasal bio. And ideally, we'd like a vaccine that doesn't affect carriage, funnily enough, because 50% of children carry the pneumococcus. If you knock out 50% of that, it's going to leave a huge gap, and we don't know what it's going to cover. Funnily enough, the pharma are not interested in a vaccine like that because all the economics are based on the herd immunity. So we're in a really difficult position where we don't want to use, we'd want a vaccine that doesn't eliminate carriage, but it will be very expensive to use.
I think there's some great concepts we can explore in the panel discussion a little later. I might just finish with one online question, which is basically about the impact of COVID, co-infections, and whether we see pneumococcus, I guess, as a secondary infection, perhaps. Would you like to just quickly touch on that point?
Tricky to answer that question. I think we saw, we definitely observed even locally a lot of pneumococcal invasive disease in that initial period after all the public health measures to reduce COVID disease. That really hasn't kind of played out as being a consistent theme. We're continuing to see associated with COVID. So we're not too sure whether that's related to the COVID or the virus circulating at the time, or was more that just people were circulating and we're seeing increased disease patterns as well at the time. So it's been very difficult to unpick, unfortunately. I don't think we'll have another opportunity, hopefully not another opportunity, to try and unpick that story either.
Great, thank you. Join with me in thanking Dr. Kandasamy again. Thank you.